Okay, this is Physics 1C for Tuesday, May 18th, and today we are going to be talking about combinations of circuits that involve inductors. And these are the names of the things we're talking about. We're going to look at a circuit that has a resistor and an inductor, and then a circuit that has an inductor and a capacitor, and then finally a circuit that has all three of our passive elements, the inductor, the resistor, and the capacitor. And we're going to look at how the currents and the charges in these circuits behave. And that's what we're doing today. Okay, so the first thing we want to talk about is an RL circuit. Just to remind you, what we've been doing for the last few weeks, in case you've forgotten, we looked at this idea of this thing called an inductor, and in a circuit, the inductor basically looks like this. It has an inductance that we call L, so L is a measurement of how strongly this coil, because an inductor at the end of the day is basically just a coil of wire. Inductance is a measure of how strongly that coil of wire can have magnetic fields induced in it. And we learned that there's an EMF associated with this that's equal to the size of the inductance multiplied by the rate of change of current within a circuit, and with a negative sign here. And what this tells us is that the inductor is going to create an EMF that is going to resist changes in current. So when the current tries to increase, the inductor is going to create a back EMF that goes opposite to the direction of the current. So if the current was flowing to the right in the circuit down here, this circuit has a battery, a switch, an inductor, and a resistor. The current of the battery would want to go this direction, but as the current increases, a magnetic field starts to arise inside of the inductor that creates an opposite EMF that we call back EMF. And that makes it so that the current can't instantly reach its maximum, but after some amount of time, that back EMF dies down, because when the current isn't changing, when you get a constant current, the inductor doesn't really do anything. Basically, when the current is constant, that means that the inductor has kind of had its magnetic field reached maximum, and at that time, it's basically just holding energy in its magnetic field. Okay. So with this idea of what an inductor can do, we can start to look at an equation for how the current actually develops over time. And in this circuit, what we're going to do is we are going to do kind of a Kirchhoff loop rule around this circuit like this, starting from here, where we're going to say when we go across the battery, if we're doing like a loop rule, so we're summing voltage drops, right? What should I write down for the battery?
It would be a positive.
Yeah, positive E, right? That's what we write down? Okay. And then minus, when I get to the inductor the resistor, going from point A to point B, we're assuming that this switch is going to close, basically, like right at the beginning. For the inductor, what do I write down? We're calling the current in the circuit little I.
Would it be negative R?
Negative
I times R?
Mm-hmm.
Right.
Negative I times R, right? So we're pretty familiar with these. And then what we'll put down here for the inductor is just this, negative L di dt. And our I needs to be this. So I basically represents the instantaneous current in the circuit. And then our goal basically is to use this to find the current as a function of time. That's our goal, is how does the current in this circuit develop? We kind of already know how it develops. We know that it's going to kind of do something like this. And I say that because we actually looked at this in those simulations, right? And when we turned on the current, I believe it looked something like this. So this is kind of our expectation. So we'd like to prove that this is what the current as a function of time looks like. And we're going to do that with this equation right here. Okay. So a couple of things to define, I guess. After time has kind of gone on to infinity, after time has allowed to go on for a long enough time, the current is eventually going to reach a steady state, and it's eventually going to reach a maximum, right? And because we're going to have this show up in our answer, let's go ahead and say what it is. What's the maximum current that we're going to get flowing through this circuit right here? And we don't need to worry about the lower circuit. We'll worry about that at the end.
E divided by R?
E over R. Yep, that's right. The EMF of the battery divided by the resistance of the circuit. And here, we're making quite a few assumptions that I should point out. We're assuming that the battery doesn't have any internal resistance. That's kind of ridiculous. Batteries always have some internal resistance. And we're assuming the inductor doesn't have resistance. Once again, this is a pretty ridiculous assumption because the inductor's made out of usually like copper wire, and there's usually a lot of it. And copper wire has resistance. Not a lot, but it has resistance that would affect some of our calculations. Anyway, if we were to include all of those things, then our maximum current would be E divided by kind of the total resistance of the circuit, right? Because the battery, if it had some resistance, and the inductor, if it had some resistance, well, they're all in series with each other, right? So imagine that we think of a resistor here and a resistor associated with the inductor. They're all in series, so you would just take this resistance plus the resistance of the inductor, and you'd add them all together. So what you could kind of assume is that this R, big R, represents the total resistance of the circuit, maybe. And in that case, it's not too ridiculous. All right, so we want to solve for the current as a function of time, and this is what we call a differential equation. To solve it, we basically want to get all of the i's together. That includes I and di, and we want to separate them from dt. So we're going to move, I guess we're just going to move this term that has di dt in it to the right-hand side. So we'll have e minus ir. How many people in here are taking, is it 220? That's Calc 3? 220 is Calc 3?
270.
No, I'm asking about Calc 3. How many people in here are taking 220 right now? Can you type 1 in the chat if you're taking 220 right now? Nobody? Have you all already taken it?
I have, yeah.
Okay.
I have.
Can you all type 1 in the chat if you've already taken it? I'm really just curious, like 1 or yeah, or you guys just say something. Did your counselors kind of encourage you to take it before you took this class? No? Okay. No, really, they didn't.
They didn't really mention it for me.
Okay. So who here hasn't taken 220? Counselors are useless here? Well, you know. So everybody here has taken it. That's super.
I mean, they wouldn't have. I guess so.
Okay, that's cool. I'm just wondering because we actually just recently sent a proposal to the curriculum at the school to we're trying to make 220 a prereq for this class. Yeah. But so a lot of you are actually taking 270 then, I guess. Is that right?
Mm-hmm.
Okay. Anyway, so many of you have actually seen these differential equations. So that's good. That's good. Okay. So maybe then you all can tell me, what's the solution to this? What's the next step in this problem? I moved L di dt to the right-hand side. What do I do next? I think your mic got stuck on, Alex. I don't know if you're using push to talk or whatever. Just
Oh, sorry.
That's okay. Just letting you know. Yeah, what do I do next here, then, if I want to solve this equation for the current? Keep in mind that E, R, and L are constants. Okay, they don't depend on. They're just constant numbers.
We can divide both sides by E minus IR.
This thing, basically divide both sides by the left-hand side. Okay.
Mm-hmm.
All right, I'm gonna do that, but I'm also gonna multiply dt to the left-hand side at the same time. Okay. So we're gonna take dt and we're gonna multiply it over here, and that's gonna be equal to L times di divided by E minus IR. Okay, so we call this kind of equation like a separable differential equation. It's separable because you can separate di and dt, and then you can just use integration. The next thing I want to do is I want to get this term to show up in our equation, and I want to move any constant that I can to the left-hand side, okay? So let's divide L to the left-hand side. So the left-hand side is going to become dt over L. And I think I want to factor an R out of the denominator right here. So the denominator is going to become di divided by R times E over R minus I. Okay. And then I can multiply the R to the left-hand side. I have to decide if I want to factor a negative out too. I don't think it really matters. Multiply the r to the left-hand side, so we're going to have r over L dt equals di over e over r minus I. And then in this form, we can integrate both sides. And what we'll get, let's see, we put some limits on here too, right? So since the switch was open at t equal to 0, we're going to say at time equal to 0, the current is going to be 0. And we're going to integrate from 0 up to the current at some moment in time. So we're going to call that I prime. On the left-hand side, we'll integrate from 0 up to some moment in time that we'll call t prime. So I prime and t prime are just arbitrary values of the current at some point in the future. And I prime occurs at t prime. Okay. Now when we do this integral on the left-hand side, r and L are constants, so they don't do anything. This integral is just going to become t prime times r over L. So r t prime divided by L. And on the right-hand side, when we do this integral, we have e over r minus I in the denominator, and we're integrating with respect to just I, where these two are constants, e and r. So what do we get out of this integral then?
Minus the natural log of the denominator.
Okay, negative log of e over r minus I.
And then we can evaluate it at the ends.
From 0 to I prime. Okay, does everyone agree with that? The negative sign came because there's a negative sign in front of the I right here. So you can check the derivative of natural log is 1 over this, and then you'd have to multiply by a negative sign because there's a negative sign in front of this for the chain rule. And there it is right there. Okay, and then we can maybe just use all this white space right here. So let's go up to like here. The next line would be plugging these numbers in. So we're going to have r t prime over L. I'm going to move the negative sign onto this side over here. So this is equal to the natural log. When I plug in I prime into this, I'll get e over r minus I prime. Divided by, when I plug 0 in, I'll just get e over r. And there really should be absolute value signs on all this stuff, right? If we're doing this properly. Is that accurate?
Yeah.
Yep.
Yeah.
Let's just do it the right way. I don't want to... Looks a little bit weird. What?
E over r is the max.
Yeah, it's always a positive quantity, right?
So it's always positive, yeah.
Yeah. So it doesn't matter, but at the same time, like, it also doesn't hurt to do this. Now, we can look at the denominator here and say, well, this it's impossible for the denominator to be... The e over r is 100% positive, right? So we can drop those absolute value signs. And then we could really use the argument that you made, which is that since e over r represents the maximum current, and you're subtracting the current at some moment in time, and the current will never be bigger than e over r, you could argue that you can just get rid of these two if you want to. So I guess that works fine. But at least in this step, let's leave them on. Whoops. Okay, so we've got that expression there. And the next thing we want to do is to basically just get I prime out of here. So the easiest way to do that is to just raise both sides to the power of e, or I never know the right way to say this. Take e to the power of each side is the right way to say that. And on the left-hand side, we'll just have e to the negative r t over L. And I'm going to change t prime to just t, and we're going to change I prime to just I, because they're really just dummy variables. When you raise e to the log of something, since this is log base e, you basically get the power, or you get what's in the argument of the log kind of just pops out. So we're going to have e over r minus I prime divided by e over r. Multiply e over r to the left-hand side. And then we just have this is equal to e over r minus I prime. And we're going to change the I prime to just an I. We could have done that in this previous line. And we just solve for I, so we're going to get that the current as a function of time is going to be equal to e over r times 1 minus e to the negative rt over L. That's it. That's the answer. Anyone have any questions? Oh, and there's one other thing we could do now, which is we could write that I of t is equal to, we could call this I max. We could just call it capital I too, I guess, if we wanted to. Because we said that E over O is I max. This is 1 minus e to the negative RT over L. Okay, anyone have any questions about this? Okay, so does this correspond to the picture that I drew up here on the right? So what do you get when you put I of 0? Let me do this in a different color. What's I of 0 equal to? Put a 0 in there.
Max current.
No. Put a 0 in for t. What do you get? You get e to the negative 0, which is e to the 0.
0.
Which is, what's e to the 0 equal to?
0. Oh, 1.
It's equal to 1, yeah. You raise anything to the power of 0, you get 1. It's kind of a definition. So if I do 1 minus 1, then I get 0, right? So the current at time equal to 0 is 0 amps. So that's on our graph, right? And then the next thing to look at is the current as t goes to infinity. And for that, we'll get, well, plug in t equal to infinity here. You get e to the negative infinity, which is like 1 over e to the infinity, which is like 1 over infinity, which is 0. So you get 1 minus 0. So here you get I max, which means that our current starts off at 0 and eventually reaches a maximum. So it asymptotically approaches the I max right here. The other thing we could do with this circuit is we can define a time constant, just like we did with RC circuits long, long ago. And in this case, our time constant is going to be L over R. And what that makes the equation look like is I of t is equal to I max times 1 minus e to the negative t over tau. Okay. And so you can ask questions like, so we call this the time constant. This is called the time constant, an RL time constant. And it allows us to get an understanding of basically how long it takes for this circuit to reach its maximum charge. And you can see what it depends on. So let's look at some of the values of what you get. This is going to be very similar to what we saw with the RC circuit. If I look at when t is equal to 1 times tau, then I'm going to get I max times 1 minus e to the negative what? If I put t equal to tau in this equation, it's going to be e to the negative what?
Negative 1.
Yep, negative 1. And if we look at what this is equal to, you're going to get that I of 1 times tau is going to be equal to I max. So plug in 1 minus e to the negative 1 in your calculator. What do you get? What do you get if you plug that in?
.632.
Yep, so about, we'll call it just 0.63. So 0.63 is about 63%. So after 1 tau, the current has reached 63% of its maximum charge, basically, right? So it's somewhere like, okay, so if this is 100%, 63% is going to be a little above the middle, so it's going to be somewhere right around here. That's going to be where this would be tau, 1 tau. Right? And once you're 63% of the way charged, you're pretty much, not charged, sorry, 63% of the maximum current. The current's almost flowing at its maximum. After about 5 tau, if you plug in I of, now you guys can't see this part down here, right? That's blocked. We'll come over here. What do you get if you do I of 5 times tau? And might as well also do I of 3 times tau too to get an idea of how this is developing. So for this one, you're going to get, it's going to be 1 minus e to the negative what? For 5 tau. If I plug in t equals tau into this equation right here.
To the negative 5.
Negative 5, okay, so plug in your calculator. What's 1 minus e to the negative 5 equal to?
Pretty much 1.99.
0.99, right? Okay, so we'll write that as I max times 0.99. Okay, so now we're pretty much maximum, right? So we can pretty effectively say that after 5 time constants, we're at maximum current. And at 3 time constants, what do you get? What if you do 1 minus e to the negative 3?
0.95.
Okay, so even then, even after only 3 time constants, we're pretty much at maximum current, right? Okay, so we can kind of think about the progression here from one. Or let me copy paste this one over here so we can put them all together. Okay, you can still see that one, right? Yeah. So the progression goes from bottom to top, right? After 1 tau, you're at 63%. After 3 tau, at 95%, and after 5 tau, at 99%. So really, what this represents is like it's telling you that it's going to take time for the current to reach its maximum. If we go back and like look at the circuit is a battery, a resistor, and an inductor, and this is the description of how the current looks, and the tau is a representation of how long it takes to actually reach maximum current. So since it's a representation of how long it takes to reach maximum current, let's look at what it depends on. The time constant depends on the size of the inductance and the size of the resistance, right? What happens to tau if the resistance becomes really small?
Tau decreases.
Tau decreases. And what happens to tau when...
Oh, sorry.
When the resistance is small, tau gets big, right?
When
When the resistance is large, tau gets small.
It's smaller.
And when inductance is big, tau is big. When inductance is small, tau is small. Now let's focus on the inductance part because I think this is really simple to understand. Can anyone explain why would it be the case that as the inductance gets bigger, that tau gets bigger? It's really just related to what an inductor does.
Yeah,
The
it's
inductor
just
slows it
slows
down.
it.
So if you have like a bigger inductance, it'll take longer for the current to reach higher.
Yeah, so that in terms of what that would look like, I think that what would happen is that your curve would do this, right? Your curve would just expand out basically if L becomes bigger, right? You're just going to increase the amount of time that it takes to get from 0 to 1 tau, right? You'll agree with that?
Yeah.
Yeah.
Basically just expanding this piece of your axis, and tau just gets farther and farther away. Okay. So again, that makes sense, as you said, because that's what an inductor does. It resists changes in current, and so if this becomes bigger, it's just going to take a longer time for the current to ramp up. So what about the resistance? Oh, and what happens when L is 0? What happens if you just don't have an inductor in your circuit, and it's just like a straight wire? How long does it take for the current to reach maximum current then?
Immediately?
Yeah, instantaneous.
Right, yeah. Now, does that actually happen in real circuits? No, absolutely not. But it's going to be pretty close to instantaneous, like on the order of probably nanoseconds or something like that. The reason why that can't possibly happen is because it's impossible for L to be 0, if you think about it. Because L is a representation of kind of how loopy something is, right? How many loops there are, how many coils there are. And even one loop of a circuit has inductance, right? It's not going to be a lot, but it has inductance. You know what I mean? Does that make sense to everyone? Okay. Regardless, point is it'll be really fast when L is small, and that should make sense. Now, what about the resistance? Why does the resistance show up here in the denominator? When we did the RC circuit, I know it's hard to keep a lot of these different ideas in your mind, especially when we're doing this all online. The resistance actually showed up in the numerator. Do you remember that? When we did the RC circuit, tau is just equal to R times C, and the bigger the resistor, the longer it takes to charge up. Does that sound familiar to you all?
Yeah.
Sure.
Okay. So resistor showed up in the numerator of this, because this one was about how quickly something can charge. But this, the resistor shows in the denominator. So what's different here? Let's see if we can understand what happens when R becomes really large. So when R is really, really large right here, can anyone explain why tau is small? If we put like a really big resistor in there?
I mean, it's an inverse relation.
Well, I mean, I don't mean to be rude, but that's kind of obvious, right? Yeah, like, yes, if R gets big, then tau gets small. My question is physically, because this is physics, right?
Okay.
What's the physical reason for
It's
that?
because the resistance slows down current.
Resistance slows down current. Okay, so how does that apply to what's going on in this overall circuit?
So the more resistance you have, the longer it'll take for the current to reach its maximum to reach its maximum value.
No, it's the opposite, right? The bigger the resistance, the shorter that it takes. Right? Because when I know this stuff's hard to think about, but when R gets big, when you have a lot of resistance in your circuit, then tau gets really small, right?
True. Yeah.
Yeah. It's only for dissipating heat. It's not about.
It dissipates heat, but it also does what Delvino just said, which is it kind of slows down the current effectively, right? I think you could say it does this, right? It makes I max smaller, right? Like if the resistance gets bigger, this will happen to your curve, right? Would you all agree?
Mm-hmm.
Okay, because the resistance is here. The bigger the resistance, the smaller the current you get. So that's definitely happening. How does that affect tau then?
Well, if it lowers the I max, then obviously it's going to take a shorter amount of time to reach a smaller like value, right? Than if it was bigger.
Yeah, I would think so, right? I think that's right. Yeah, I think that's a very good observation. If this becomes smaller, like this, there is a smaller change, right? There's a smaller change between 0 to I max, right? Would you all agree with that?
Mm-hmm.
Yeah.
So you affect this, right? You affect di. The change in I is what you're right?
Mm-hmm.
And I think that then has an effect on this. Because then what's going to happen to EL? If this gets smaller, then this gets smaller, right?
Mm-hmm.
And now if the inductance, this is back EMF, right? I know it's really hard to follow this whole train of thought, but this is back EMF. So if this is smaller, then the circuit's going to be able to reach its maximum current faster. So not only will this happen, not only will the current go from this to this, but at the same time, that's actually going to do this too. So both things happen simultaneously because the resistance ends up affecting di, which affects the back EMF, which then affects tau, basically. So yeah. Oops, I didn't mean to do that. Anyway, anyone have any questions? I've completely ruined my diagram. Anyone have any questions? So this is the LR circuit. This is you could think about it as like charging up. It's not really charging up. It's reaching current, but yeah. So we'll do a problem with this. Let's do the problem first, and then we can do the decaying version of this. Anyone have any questions? Does that all make sense? Okay.
Yeah, just processing the resistance.
The thing about the resistance? Yeah, do you all want to say anything more about that, or does anyone have any comments about that? As to why big resistance...
It kind of
means
seems
more.
counterintuitive.
It is, yeah, yes, it is counterintuitive, right? Yeah. Especially if you compare it back to what we learned before, right? It's kind of counterintuitive. You kind of almost would expect the R to show up in the numerator, right?
And the other type of circuit, the resistance gets higher, then it takes longer, but here it's the opposite.
Yeah, exactly. Now, in the RC circuit, what was happening was you're charging a capacitor up, right? And what the resistance would do in that case is it would make it take longer for the current to actually get onto the capacitor plate. You know what I mean? It would actually just increase the time interval because think about it as like, you know, the resistance acts like friction. So when you're trying to like push charges onto a plate and there's more friction, it's going to take longer, right? Because they're just not going to be able to reach the same amount of energy. Excuse me. So, yeah, it is kind of backwards here. I don't know if this helps you at all to look at this, but if you look at the dimensions of L, the inductance L, L is measured in henries, but it's actually also measured in ohms seconds, ohms times seconds. And resistance, obviously you know that resistance is measured in ohms, right? And capacitance is actually meant, we didn't talk about this ever, but if you look at the units for capacitance, you can prove, I'm pretty sure capacitance has the dimensions of, okay, I was going to say 1 over ohm seconds, but that can't be right. I think it's going to be ohms over seconds or something. Let's figure it out. So what is a capacitance? Capacitance is, we get it from this equation. C times delta V is equal to Q, so Q over delta V is equal to C, which is a coulomb divided by a volt. But a coulomb is an amp second, and a volt is just a volt. And an ohm is a volt over an amp from this equation. If you take delta V over I, you get R. So that means that V over A over V would be 1 over ohms. Yeah, it's seconds over ohms. That's what it is. Okay. Seconds over ohms. Okay. So capacitance has units of seconds divided by ohms. Okay. So if you look at these values, it kind of makes sense that if I do R times C, I get time, right? Because the ohm times seconds over ohm, you get time, right? And then with inductance, since inductance is ohms times seconds, and resistance is ohms, well, there's only one way to get seconds out of this, right? L over R.
True.
So, I don't know if that helps at all in terms of understanding it, but this this is pretty interesting. I mean, just apart from what we're talking about, just like as a side note, like this kind of progression of inductance, resistance, capacitance, all having something to do with ohms and time, that's kind of, I think, a little bit like this is I think this is pretty interesting, right? It almost kind of, it hints that there's something going on with these quantities, right? That they're all connected like this. Like,
yeah.
This is second to the first power. This is seconds to the 0 power, and this is seconds. Oh no. Okay, that's really interesting. So it's the ohm. The ohm is the one that's changing, right? Sorry. No, there's no like simple pattern though, is there? Because this is like ohm to the first power, and this is ohm to the -1. But yeah, the reality is that what we're going to learn on our next chapter is there's a way to think of each of these things: inductance, resistance, and capacitance. There's actually a way to convert these into a common unit that we're going to call impedance, basically. And it's only really going to apply when we talk about AC circuits. So that's going to show up in the next chapter. Anyway, so okay, let's look at a problem that we can use to solve with this. 2:37. We're doing fine on time. All right. Sensitive electronic device with a resistance of 175 ohms is to be connected to a source of EMF with negligible by a switch. The device is designed to operate with a current of 36 milliamps. I'm going to assume that's probably the maximum current, so we'll just call that Imax. But to avoid, the device is designed to operate with a 36 milliamp current, but to avoid damage to the device, the current can rise to no more than 4.9 amps in the first 58 microseconds after the switch is closed. So this is, yeah, we'll write that down in a second. An inductor is therefore connected in series with the device. That's kind of interesting. You know that you can't have the current spike too much within this time period, so you just add an inductor. It's kind of clever. As in figure 30.11. So same picture with the switch S1 closed, I think that's what it says. Yeah, the switch is S1, this one. Okay, so what is the required source EMF E? What's the required inductance? And what is the RL time constant tau? Those are the three things that we want to calculate. All right. So how can I use these other two pieces of information? Let me give you all just a second. Why don't you all just read it? Take a moment to think about it, and tell me after you're done how I'm going to use those two pieces of information right there.
Isn't that your start rate of current changing?
Mm-hmm.
You could think of it as an average rate, maybe, but
Yeah, it's an average rate.
I don't know if that's necessarily going to be how we're going to use it.
we can like solve for a variable.
What variable?
After 58 microseconds.
Can we use this equation that we just
We only
derived?
know resistance.
Yeah, we could use that.
Imax.
Yep, we have resistance. That's good. That's right there. We've got I max, yeah. What else do we have?
We have little I and T.
Yeah, we do. That's what these are. This is giving us a current and a moment in time, right?
Mm-hmm.
So we can basically use these to solve for, I guess,
yeah.
L, probably, right? Yeah. Okay, so let's do that. So we have, we know that, I'll put it right here as a known. We know that the current at 58 microseconds, so that's 58 times 10 to the minus 6 seconds. We know that the current at that moment in time can't be bigger than 4.9 milliamps. It should be 4.9 times 10 to the negative 3 amps. I should also mention that 36 milliamps is going to be 0.036 amps. Okay, so let's solve for L. I kind of want to solve it without using the numbers because we have so many scientific notation things here, and let's just plug it in at the end. So we'll just take I of t, whoops, let's use the same color as the equation. Okay, so we'll take I of t divided by I max. I don't know why it occurred to me just now, but I can't wait until we're back in person so I can actually do the stuff on a chalkboard instead of use this thing. All right, I of t over I max. Let's see, that's equal to 1 minus e to the negative. You know, whatever. I was going to say, we could actually solve part C here if we wanted to. Immediately.
Mm-hmm.
Doesn't
We
matter,
can
though.
get a whole bunch of stuff, yeah.
Doesn't matter, though. Let's just, we'll just solve for L first. We'll go in order. Okay, part A is actually really easy, isn't it? I just realized that. This is part B. Part A is super simple. It says, what is the required EMF? We know that E over R is equal to I max, right?
Yeah,
So
yeah.
So then this is going to mean that E is equal to I max R. So E is equal to 0.036 amps times 175 ohms. Okay, someone can maybe calculate this for us while we're doing this. Okay, so I have t over I max, 1 minus e to the negative. Here we plug in RT over L. For part B, we want to isolate L, because it says what is the required inductance. So we'll solve for L here. So we're going to get 1 minus I of t over I max is equal to e to the negative RT over L. Make some space, because we now need to take the natural log of both sides to get rid of the exponential here. So we'll have natural log of 1 minus the whole right hand side is going to become negative RT over L. So we solve for L by taking, basically multiplying, dividing. So we're going to get L is equal to negative RT divided by natural log of 1 minus. Okay, did I do that right? So we divided by I max, that showed up here.
Yeah.
We logged both sides, so we got that. And then this natural log, basically you just take the power and bring it down in front, or however you want to think about it. You get this. And then we basically multiply L over to this side, and then take this piece, divide over here. So it looks right to me. Okay. Any questions about that? Now we plug in our numbers. So it's negative R, which is 175 ohms, times T. The information we have for T is that the time is going to be this time. So 58 microseconds. All divided by the natural log. So we assume that this natural log is going to have to give us a negative number now, right? And it does, because 1 minus this quantity is guaranteed to be less than 1. So we're going to be taking the log of something that is between 0 and 1. And since it's less than e, that means that the answer is going to be negative. That's good, because we want it to be negative to cancel out with this one. So negative... So I of t was 4.9 times 10 to the negative 3 amps. That's the time at which we knew what the current was. So we put 4.9 times 10 to the minus 3 amps divided by the maximum current, which is 0.036 amps. This is good. You always want to have, when you're doing a log, you want to make sure that the thing you're doing the log of doesn't have units, right? So that's good. So what do we get for L, and what do we get for E?
For E, it's 6.3 volts.
Okay.
And L is 6.94 times 10 to the negative 2.
So 0.0694.
Yeah.
Now the unit for this should be Henry, and look at it as because ohms times seconds is Henry. Let's say Henry. So I'll just put capital H here. It's actually a pretty big inductor. Anything over millihenry is a pretty big inductor. That's it. These problems are pretty easy. I mean, I don't know how easy doing the algebra is here, because anytime you have to do logs and stuff, I know that's maybe not something you're super confident with, or maybe you are. I don't really know what your education was, but it's mostly just algebra, right? And anything that just involves algebra tends to be pretty easy in physics.
Mm-hmm.
All right, anyone have any questions? A, B, C. What is the RL time constant? Well, this is super easy now, because we said before that tau is equal to L over R. So this is equal to 0.0694 Henry divided by 175 ohms. And yeah, we could have probably just solved for this first. It would have made the calculation a little simpler, but not by much. So I get that this is something like 396 microseconds, 397.
Yeah.
That's what I got. Just gonna make sure that's right.
.396 microseconds.
Yeah. All right. About 0.4 milliseconds. Does anyone have any questions? All right. If not, before we take a break, let's just quickly go over the other side of the circuit right here. So the other side of the circuit would be what happens, so I'll just read it right here. Closing switch S2 while opening switch S1 disconnects the combination from the source, from E. And what's going to happen then? So if I open S1 and I close S2 at the same time, what's going to happen in my circuit? So if I open S1 and I close S2.
L is going to want to keep the circuit moving.
Yeah. Since the current is going to tend to decrease at that point. And why does the current decrease?
I mean, it's taken off its EMF source.
That's part of it. Yeah, you need the EMF to keep driving the current through the circuit. What is naturally causing the current to decrease in the circuit, though, whenever you close the switch?
There's a new path.
There's a new path, I agree, but what's actually making the current go down? Another way to ask the question is, how is the energy decreasing? The resistance, yeah, exactly. The resistor dissipates energy out of the circuit in the form of heat, right? And so that's why you need the source to keep energy pumping through it, right? To keep electricity pumping through it. But the moment you don't have a source, now the current is going to collide with the current is basically charged particles that are moving. It's going to collide with the elements of the resistor, and those charged particles are going to lose energy. And that's going to make the current decrease. But as you said, the inductor doesn't like changes in current. So the inductor is going to produce a forward EMF that's going to keep the current flowing up until it no longer has a magnetic field. The way that I think about it is that when the current has reached its maximum, before we do this process of opening, there's a big magnetic field that's contained inside of the inductor, right? That magnetic field starts to act as a source of current whenever we remove the source. Because now that magnetic field has energy, and the magnetic field can basically decay. And in the process of the magnetic field decaying, it's going to send energy into the circuit, which will keep the current going up until the magnetic field no longer exists. Okay, does any of that make sense? Does anyone have any questions?
I guess that makes sense.
All right, so we can go through. I don't know that we even really need to go through the derivation of this. I could just show you the answer, but we might as well. Can't guarantee that I'm gonna get this one right though. So we want to go. It doesn't really matter which direction we go, right? But let's go this way. So now here what's happening is that S2 has been closed, but S1 has been opened. We have current flowing around like this. We're going to do a loop roll again. When we go from A to B, we're once again going to get negative IR. And this one, I don't know what I write down. I mean, I think I still write negative LD IDT. I think this is the right thing to write down. And now we need to solve this differential equation. It's pretty easy to solve, though. So I should probably kind of title what we're doing here. So we're using this. This is our equation. That was our loop. So this is current decay. Okay. So there's our equation. I was trying to think for a second if I should make this positive. But I don't think we need to. Because if the IDT is negative, then this will automatically become positive, so I think it's fine. But it might not be fine, we'll see. Okay, so we get something like this. We multiply the dt to the left-hand side, get negative dt r over L equals di over I. Integrate both sides. The left-hand side becomes just negative tr over L. Right-hand side becomes the natural log of I. We have to have limits on these things, so we're going from 0 to I prime. No, that's not right. What should my limits be now?
Uh-oh. It should be I max.
Yeah, we need to start at I max down here because we already reached our maximum current, and we need to go to 0. No, we want to go to I prime because we don't want to get an answer. We have to go down to some current. Yeah. And then we'll look at the limits. And then the left-hand side has to go from... This doesn't matter. We can go from 0 to t prime now, right? I think that's totally fine. Because we can basically just say at t equal to 0. Whoops, this isn't the loop we're doing. We're doing this loop. At t equal to 0, we open S1 and close S2. That's t equal to 0. So t equal to 0 is going to correspond to I max, and then t prime will be whatever the time is at which the current is equal to I prime. That works. Okay, so then we do our integral here. The integral on the left is just going to become negative t prime r over L when we plug in the limits, and the integral on the right is going to become the natural log of I prime over I max. Right?
Mm-hmm.
Move the log down so that we can see that it's actually applying to the whole thing right here. I prime and I max pretty much have to be positive, so I don't think we need to worry about the absolute value signs. So now we just say e to the negative tr over L is equal to I prime. Well, we drop our primes now, I guess. Might as well move the I max over here, and that is the answer. So our answer is basically that the current as a function of time is equal to I max e to the negative tr over L.
Okay. Looks a lot like a term in the current growth.
Yeah, exactly. It's just the other term, basically, right? So now it works out that when we take I of 0 You put 0 in here, e to the 0 is 1, so you get I max. That's what we expected. And when we let I of t going to infinity, then we get 0, which is what we expect. And the reality is that it will happen faster than infinity, obviously. And if we plot our current, I, versus t, now what it's going to look like is a decaying exponential where, let's say that this is I max. Then the curve is going to come in this way and then kind of go down like this. And asymptotically approach the axis down here, like that. And we saw this. We saw both of these behaviors when we looked at these things on PhET. We can pull them up again and see them. That when the current was turning on, it would go like this, and then when the current was decaying, it would kind of go back down like this. Exponential growth, exponential decay. It's really amazing how often this number shows up in physics. You know? We're describing physical systems. It just shows up so frequently.
It's everywhere.
And of course, I mean, if you understand the math, you understand why. It's because it really just is because this became a natural log, right? So, but really, yeah, I mean, it really does show up all over the place. It shows up in radioactivity, showed up in RC circuits, it shows up in if you're talking about this is the exact same equation you would get. Actually, this one, sorry. This is the exact same equation you would get if you were trying to describe the velocity as a function of time of a skydiver. It would look exactly the same. You'd have v of t is equal to v max, which would be the terminal velocity, times 1 minus e to the negative stuff times t. And stuff would be related to drag coefficients and stuff like that, basically. It's the exact same equation. Because a skydiver would have a velocity as a function of time that would look kind of like this. You'd start at 0, and you'd eventually reach your maximum, right? So, pretty similar phenomena.
Is there anything in physics that like decays kind of on the order of a polynomial?
Well, I
It's
mean,
like
this can be written as a polynomial, obviously.
or a finite polynomial, I guess.
A finite polynomial. I'm sure you can construct systems where you feed a function in, where like you have a magnetic field, for example, that you make it decay as a polynomial or whatever. I mean, we looked at a problem like this last time, right? Where there was a magnetic field that was a polynomial function, but it was kind of a problem that was anyway. Trying to think of a better answer to your question, though. I mean,
It's like nature is like always exponential.
it's not always exponential. There's definitely lots of features in nature that don't follow these exponential rules. Like projectile motion is the first one that occurs to me. I mean, that's a polynomial description of the y coordinate, right? Anyway, this is a good place to take.
Yeah, I guess so.
It is, right? Yeah. So, yeah, good time to take a break. We'll take a break until, we'll say 3:10. But does anyone have any questions before we do that?
All good.
Alrighty.